For page 81, you are going to paste in the notes that says graphing exponential functions. We've got a few parts that are highlighted here, so you'll also highlight these. And so these are the same transformations that we've actually already worked with. So this is going to be a review from our chapter 1 on transformations. So if you remember the a out in front, so our parent function here is b to the x. So I have that highlighted and I have that box. That's the parent function, b to the x. And so here we have this a out in front that multiplies it. This is going to be our vertical stretch. It does not have anything to do with this exponent at all. It simply sits here by itself. So this is going to be a vertical stretch or a vertical compression. Remember that it's a vertical stretch when a is bigger than 1, but it's a vertical compression when a is between 0 and 1. This here on the at the exponent with the x minus h is either going to be a horizontal shift left or right. It's going to go right if h is positive, and it's going to go left if h is negative. Then we have your plus k, our last highlight. This is going to be your vertical shift up and down. So this is going to go up if k is positive, down if k is negative. But this is also going to determine where your horizontal asymptote is. So typically your horizontal asymptote is on the x-axis, y equals 0. So if you move it up or down, if you move the graph up or down, you're moving the horizontal asymptote as well. So how much ever you move it up or down is going to determine where your horizontal asymptote will now lie, and that is going to be the value of k. So we have an example here, 3 times b to the 2x minus 4 minus 1. So our parent function then is going to be 2 to the x. Our vertical stretch is going to be by 3. It's going to move right 4, and it's going to move down 1. This also means that your horizontal asymptote is now going to be at y equals negative 1. For this one, they took their parent function, instead of just 2 to the x and making a table for 2 to the x, they actually took the parent function as 3 times 2 to the x, which is fine as well. Typically, we didn't do that when we were doing chapter 1, but that's not a big deal. It will still give us the same answer for our final graph. So if you use your parent function as 3 times 2 to the x, we're going to make a small little table here. You'll plug in x equals 0 to find out where your y-intercept is going to be. So if you plug in 0 here, 2 to the 0 is 1, times 3 is 3, so a point is going to be 0, 3. They plugged in 1 as well. You plug in 1, you get 2 to the 1, that's 2, times 3 is 6. So here's 2 points. We usually use about 5 points, but this is fine using 2 points. And so the 3 has been accounted for with that vertical stretch, so we don't have to put a 3 in front of our y over here. Typically, we would have written this as 3y minus 1 to do with the vertical stretch of 3 and the going down 1. But because of the parent function they chose, we don't have to put that 3 here now. We're going to have these points that were already multiplied by 3, so we don't have to worry about it. And so over here, in order to make these points go right 4, we're going to do x plus 4 for your x's. That becomes 4 and 5. In order to make it go down 1, we're going to do y minus 1. So 3 minus 1 is 2. 6 minus 1 is 5. So you have 2 new points now for your transform function. You'll graph those here, and then you'll connect your dots. Remember, your horizontal asymptote was at y equals negative 1, so we're going to put in a dotted line there. And you'll notice that you have exponential growth here. And the reason we have exponential growth is because our base was 2, and this is bigger than 1. And so that's right here. It says you have exponential growth when the value of b is greater than 1, but you have exponential decay when it's between 0 and 1. So this really shouldn't say b is less than 1. It should say that it's between 0 and 1. And that is it for this page.